So I think everyone's here that's going to arrive. So if you go to this URL, you can find all the slides today. So if you want to follow along on your phone or I go too quickly, you can go back. The example code is there. The further reading links are there as well. It's just like a gist. So today I'm going to talk to you about OpenTracing, distributed tracing. And at the end, if you're asking me any questions, you can watch me squirm and avoid giving the consultant's answer to any of the questions that you give me, because I am a consultant. And this means a few things. So the first thing is that people are looking for value from me as soon as I go on site with them. So I'm always looking for technologies which give me those quick, easy wins that I can iterate on and really give something back to people that I work for really, really fast. And tracing is my favorite way to do this. So I first heard of tracing in coordination with these three things. It has a name which is somewhat controversial, so let's not say that name. But this is a personal favorite technology for me because it works anywhere that you can run some code and make a TCP connection out. So I just did this for a company called Daisy. Now Daisy are a organization who bring together creative people. So if you're looking for a graphic designer and you are doing a logo for something, you can find them through this and you can work together on a project. So we took them from essentially having, they had 2 log messages, I think, when we arrived. And when a request came in, it said request received. And then when the request went out, it said response sent, which isn't very useful. So what we did is we used this technology to take them from this to doing an AI-driven alerting system using trend analysis on previous results. So we did that using these technologies. They had a bit of a mixed stack, so most of their stuff was in AWS Fargate. Some of their stuff was on Lambda. We actually did the alerting and tracing into Datadog. Mostly today, though, I'm going to be talking about open source things, so you can go away and play with these on tomorrow and convince your boss to use them at work. So I'm going to start off and talk about kind of what the current state is of the tracing market, what you get if you type tracing into Google and what that means. And then I'm going to talk about some primitives relating to a specific implementation. So I'm going to talk about the primitives of open tracing, and then we're going to move on and we're going to look at how you implement something. So if you type tracing into Google, this is what you get. So there's a whole bunch of companies up there. So let's see, we've got Honeycomb.io at the top, we've got Datadog, we've got Jaeger, we've got Lightstep, we've got New Relic. Google Cloud has a stack driver trace system. Azure have a tracing system that I couldn't find that much about. We have X-Ray from AWS. We also have OpenCensus, which is the circular-looking one, and the hexagonal one, that is OpenTracing. So of these products, these two are a little bit different. So these two are open standards, and what that means is that anyone can implement a client for these types of tracing systems. And a lot of people have. So these companies have implemented an OpenCensus client, and these companies have implemented an OpenTracing client. So I have most experience with OpenTracing rather than OpenCensus. However, there's been some very exciting news, and that is that these two standards are going to be merging. So what this means, in practical terms, is we're probably going to have one standard in the coming future, which is going to be able to do tracing across pretty much any platform that you're going to be doing it in. There's a link to this article, by the way, in that page. That's a link to at the bottom of the slide. So I'm just going to give you a little bit of explanation as to what the history of the tracing market is and kind of where we are at the moment. So who here has heard of Simon Wardley? A few of you? Cool. So Simon Wardley has a whole bunch of articles on like predicting the future essentially in business. He calls it playing chess with maps. So this is one of the things that he has put together from research. It came out in about 2007, so more than 10 years ago now. And what it does is it uses some research he did into boom hype cycles, which is kind of like, and what sort of media surrounds them to predict where a specific market is. So let's kind of talk through these different bits. So at the bottom we have the Genesis section. During the Genesis section we will see a whole bunch of media articles about like how fantastic this new bit of research is. It's really cool, it's going to revolutionize our lives, and it kind of glosses over that it's a bit shit at the moment. So we then have... in this section, this was really Google's Dapper paper, which kind of kicked off all this stuff for the kind of tracing market. And next we have the custom-built section. Now, in this period of time, you will go to conferences and you will see people talking about how to build an open tracing solution. People, in this case, people are kind of iterating quite quickly. They're changing how they are doing things in their application and how they do their tracing. So this is where that kind of section is. So in about 2011, 2010-ish, I can't quite remember when, we were doing this at B-Sky-B. We were implementing our own tracing system. I would love to say that I was a lead on that project and it was my wonderful idea, but I was a junior dev at the time and I've only just got into programming. So next we move into the section where roughly kind of the tracing market sort of is, which is in the product section. So in this stage, tracing is kind of going to become common. The articles are talking about how to use specific products, not necessarily like how to implement things, but you should use this thing. In fact, this talk today fits into that category. And it actually works, and we talk about how to use it. So let's talk a little bit about the history of the products which are out there, which are open source. So we have, way back in 2010-ish, we have Twitter had a whole bunch of problems with their website crashing all the time. Who remembers the fail whale? Yeah, I remember the fail whale. In order to work out what was going on, what they did was they implemented a tracing system called Big Brother Bird. Big Brother Bird eventually was open sourced as Zipkin, which some of you might have heard of. And then eventually, after about 2 years, the Zipkin project kind of got a little bit less active. It was being found that lots of things weren't really being merged, lots of pull requests kind of weren't happening. So some people went away and they rewrote the Zipkin server with far less dependencies to make it a lot easier to deploy and a lot easier to use. This kind of happened around 2015, and this is OpenZipkin. OpenZipkin, the ideas from OpenZipkin and all these things were then picked up by Jaeger, which is the client that I'm going to be talking about today. Jaeger was released by Uber, and it's like an open source tracing product. And so we can actually still see the history today of the Big Brother Bird project inside Twitter, because the HTTP requests which have been traced in the headers, you will actually see annotations which are B3. Which stands for Big Brother Bird, which is kind of interesting. And finally, we see kind of this last section. Now, this last section is the utility section. And this is where things are becoming really, really ubiquitous. And this doesn't necessarily mean ubiquitous in the sense that everyone has one. It means that the market is reaching kind of its limit. So in this section, we see see articles being published which make the assumption that you have this technology in your stack. So I would probably say that databases are kind of here. So all publications about like writing microservices and things assume that you're probably going to be using a database at some point. So this is where open tracing comes in. In order to make this happen, we need to see open standards so we can chop and change our service providers. And this is why we're getting this merger between OpenCensus and OpenTracing at the moment. And this is why this technology is particularly relevant. So there are some exceptions to what's happening in this market, and that is X-Ray and New Relic. Weirdly, neither of those support open standards. You can export to OpenCensus, I think, if you use like an add-on for X-Ray in your code. Okay, so enough of that. So I really like OpenTracing. So the reason that I like OpenTracing is because it's used in a lot of the technologies that I use on a day-to-day basis. So Istio, Trafic, Linkerd, they all support starting traces in their actual software, so you don't have to go into your microservices. You can start at the edge of your network. It comes in open and paid format, so I work with lots of different sizes of organization, and some organizations can't afford to pay for a really expensive service, or they don't have the authority to say, I want to buy this. So this gives us options to get tracing into the systems, and also the coming merge with OpenCensus is pretty exciting. Okay, so what are tracing systems? So we've talked a lot about abstractions in this conference and how we are dealing with abstractions from the sense of where our code is running, but also like in how we are working. So the biggest abstraction that always comes up with technology is that most people, when they look at a website, they don't think of it as a website which is running on a server. They think of it as something which is running in their browser. And those browsers, if they're particularly switched on, they might know that it talks to a server, but largely that's going to be abstracted from them. But the truth is that our world is really, really complicated. So we need a technology to understand this, which is going to work at the same level of abstraction that we do, which is not necessarily servers, but microservices, nanoservices, functions. Also physical servers if you've got an actual application running on that. So what I mean by that is we need a sort of tracing system which is going to trace the actual unit of work which is flowing through our system. So I'm going to talk you through like a little bit of an example now. This is an example of the banking system, and I'm going to introduce you to some kind of tracing terms as we go through. If you want to go to this URL, examples, links, etc., I would recommend opening the the Jaeger page. Okay, so a request comes into our system. It comes to Trafic. Trafic is a service registry. And once it goes through Trafic, it's going to hit our customer microservice. Our customer microservice, by the way, don't think of these as a single container. Think of them, or a single application which is running in a Lambda. Think of them as collections of related bits of code which are running as a logical unit. So it hits the customer service. The customer service is responsible for names, date of births, kind of anything relating to like customer details. It has some state. It has a Postgres database. By the way, so each of these little highlighted bits here, they are called spans. They are logical units of work. This is true across all tracing systems. They use the same terminology. So as soon as the request hits Trafic, we start doing a span. When the request, just before the request leaves Trafic, we start another span. And as the span comes into the customer service, then we start another span as well. All of these things together are called a trace. And these traces get sent to a tracing server, although the actual implementation of this isn't defined as part of any of the standards. So we just had a talk on scalability, and one of the key concerns with any of these is either keeping costs down so that you're not spending loads of money on logging things that you're not interested in, but also in certain circumstances preventing yourself from DOSing your own servers. So we can actually handle that with OpenTracing by telling the tracer to only send on specific headers, or really usefully, only sending given a specific probability. So you can say that you only want to trace 0.1% of your request, 0.1 of your request, which is 10%, or 0.01, which is 1%. So this is actually one of the key differences between this technology and metrics, by the way. So the fact that you sample the requests rather than necessarily recording every single one of them. You can also do things like reduce the request based on the latency you're receiving. Okay, so let's have a look at another service. So request comes into Trafic, goes to the account service. The account service is responsible for mapping customers to account. You can imagine that it's got some logic in there about like whether a customer can open an account or not, whether an account is still active. It has a Postgres database again. So that one was pretty simple. Let's do something more interesting. So let's talk about the cashier service. So the request comes into Trafic again. The request goes to the cashier service, and you'll notice the cashier service doesn't have any state. Now, the cashier service is responsible for taking and receiving money. So when someone makes a transaction, it goes into the cashier service. So this is modeling something which is a truth of the banking system, but is a lie that we are frequently told in software development. So when I was learning about database transactions, my teacher said to me, Billy, so what happens is when you try and take money out of your account, we start a transaction and then we withdraw the money from the account and then we commit the transaction, and then if you don't have enough money, we roll it back. It's not what happens at all. The banking system is much more terrifying than that. So what really happens is records get written to CSVs, which get SFTP places. So it's a massive distributed network of computers all working together to create a contiguous whole. So actually what it is a queue-based system, albeit using slightly strange technology. So what the cashier service does is it fires an event into the transaction service. Transaction service simply keeps a record of all the transactions that are in the system. And in order to do that, it queries the account service to check if the account is valid that it's going to write the transaction to. And when it's finished, it's going to fire another event, which is going to go to the balance service. The balance service is responsible for maintaining an edge cache of all of the current balance. So this is a pattern, I think, called CQRS, in that we have our command over here and we have our query over here. And when we put this into OpenTracing, this looks like this. So at the start, we have Trafiq. So Trafiq receives the request into its TCP connection. We see the request coming into going through a TSL step, and then we go to hitting the actual backend. The actual backend which connects to one of the internal services. So as the internal services run, we have it goes to the cashier service, because this particular trace is that last one we looked at, and the cashier service does a little bit of processing, then emits an event. The transaction service then consumes that event and does a GET request to the account service, including, and then the account service does some SQL. And we see the transaction service doing an SQL select again once it's got the message back from the transaction service, and we do an insert, and then we emit another event which goes down to the balance service and then goes all the way through to the write a value into the Redis server. And this can also kind of look like this. So this is the same data but represented as a graph. All of these spans come together to form a data structure which looks like this shape. It's a directed acyclic graph, a DAG, which always reminds me of dogs said with an Irish accent, DAGs. So here we have the first two. They are the Trafiq service, Trafiq, and then we have the cashier service, and the next huge group, that is the transaction service, and the top ones are the account service, and the bottom ones are the balance service. So the next few things that I'm going to talk about are specific to OpenTracing. So OpenTracing consists of three things. It's a client interface that you can include in your code and reliably build instrumentation for specific libraries around. It is a semantic specification which tells you about how the data inside that client interface is to be represented. It says things like, this should be a directed graph. And we have the semantic conventions. Now, the semantic conventions are keys that you can set on specific bits of data that you want to include in the span. So there are kind of four kind of primitives that are worth mentioning at this point. So these are part of the semantic specification, but also appear in the client interface. So we have spans, references, span contexts, and tracers. So spans, these bits, right? We've kind of talked about this already. References, they're how they relate. And the tracer is what actually sends the data out and implements this specification, and it goes to whichever server. And finally, we have the span context. Now, span contexts are used because you can put data in spans, and the sort of data that you might want to put in a span is this. So, kind of HTTP method, if you're connecting to a database, which database you're connecting to. You can also indicate that a span has had an error. And once a span has had an error, you can attach extra information to it. So you can attach logs. And what logs mean is that you can have like a backtrace or additional information in your tracing application, so you can start debugging straight away where the application has gone wrong. There is also baggage. So I've never used baggage for anything, but apparently you can store random stuff in there. Mostly it is used for data which needs to be available on multiple servers in the trace. It normally consists of the span ID, the trace ID, and if there is a parent span, the parent span ID. Okay. So I've mentioned quite a lot about kind of the technology. So how do we go about like implementing this in a specific bit of code? Again, so if you want to open up some repositories to follow along the code, which I'm going to show on the screen, then you probably want to go to and open up the cashier repository and also the transaction repository. Okay, so my strategy is almost always this. So I'm targeting the lowest hanging fruit first, and then I'm iterating on that. So the first thing that I'm going to do is I'm going to go to the edge of the network and enable any built-in tracing that I have. If you are using kind of something like Amazon Lambda, you're going to have quite a lot of tracing built into that if you decide to use tracing doing X-ray. So you can already get a lot of tracing for free. If you are using something more custom, if you're using things like Knative, then you're going to have to do a lot of this work yourself. You can get some tracing out of Istio, which is kind of cool. And next, we're going to do some simple enabling of tracing inside a Python application, and then I'm going to show you like how, if you don't have any instrumentation available, that you can add your own instrumentation to a specific call of particular interest. Yeah, so use registries and meshes for this. I'm sure a lot of you are using these already, but they almost all come with tracing for free. You get some tracing on the edge of the application. If you're using like kind of a basic application, use something lightweight like Trafic. If you're doing something like kind of cool and complicated, then use whatever's applicable, but like Istio is a good shout for that. Yeah, so these will all add tracing data to your application. I couldn't find out about the Microsoft one or not, but it works. Okay, so we're going to start off by talking about the edge of the network. So our edge of the network is this, the Trafic microservice service registry. It looks like this. If this has gone red, that means my demo is broken. Help. And I configured this by doing this. Well, that's not actually true because I don't really like editing files, so I configured this by doing this. I'm a big fan of Kubernetes. It's not very serverless, but this is how I installed the application. So I did tracing enabled, and I gave it the host of my Jaeger install and things like this. You can do this with like a pre-provisioned like system, like Lightstep, like Datadog. You don't need to install your own tracing system. And what we get when we enable tracing, when we set that config, is this. So we can see that requests are coming into Trafic, and that's it. But this is already some observability that we can add into our application at doing pretty much no work, right? It's just changing one configuration value. So we can start, based on this, doing monitoring. So we can identify how many requests are flowing into our application. We can start triggering alerts if it drops below a certain rate. We can start identifying which of these requests are 500 errors, are 404s. We can see if they're taking a particularly long period of time. So we're already starting to get some observability into our application. Albeit, we could maybe do this with a load balancer, right? By looking at the logs from that. So that's not that exciting. Let's do some actual tracing inside an application. So I'm going to show you a Python application because that is what I most recently did. This is a Flask application. It uses a few different libraries. So it uses requests, which makes HTTP requests. It uses SQL Alchemy, which makes SQL requests. It uses Redis to make Redis calls. And there's a fourth one that I can't remember that I'm sure I'll remember in a sec. So the kind of way that you configure packages in Python is using pip files. goes to build the pipenv, which is like an isolated development environment for Python. So in this case, we're initializing the Jaeger client because I'm going to send data to the Jaeger tracing service. We're initializing 2 tracing libraries. One which is called OpenTracing Instrumentation. This is the main library we're going to use, and also Flask OpenTracing, which is going to take the requests which are coming into our Flask app and turn them into spans and things that we can use and send to our tracing application. So this is how you initialize the OpenTracing. By the way, if you want to follow along with the code, this is in trace.py on the cashier service. It's also on all the services, but this is where this is from. So what we can do is we can then set our tracer to output at a probabilistic rate. This is set to 1 at the moment, so that everyone can see logs as they go through the system. And we also provide a service name, and we initialize the tracer. Now, if you're actually doing this inside a Lambda function and you wanted to use, say, OpenStack, you would do this. So you wanted to do this inside a function, cloud function in a Google Cloud, you would do this. So the API calls are really, really similar. The main difference is that we're using OpenCensus if we're inside Google Cloud. I have most experience with OpenTracing. So we've now got a tracer up and running, so we want to start doing something with that tracer. So we're going to install some patches. So in this case, we're going to install patches for all our requests, and we're going to install then hook into the Flask application. So in this case, we're going to do patch the requests library. So we're going to patch the request library and add tracing to it, which is going to mean whenever we make a HTTP request, the span goes to the other server. And we're also going to patch the Redis and SQL Alchemy libraries. And we're also, then after that, we're going to add some tracing on top of the Flask application to make sure that all the requests that come into it get turned into actual traces and things that we can pass around the system. So when we make a request with a request library, it's picked up on the other services. So I'm going to talk a little bit about implementation details now. So this is how you do an annotation in Python. And what I'm trying to illustrate here is that when you add tracing logic to your code, it shouldn't be mixed in with the rest of your code. It should be easily removable because it is very hard to test. It is literally only side effects. There is no conceivable thing that you should see in the rest of your application. So what I'm doing here is I am actually going to the Flask tracer. I am going to take the current span that the Flask tracer has picked up, and I'm going to send it to the OpenTracing instrumentation library so that we can get those 2 libraries integrated. And what I'm going to do is I'm going to wrap this around each of my functions which get called to initialize the application. And then I'm also, where I set up my application, I'm going to start using the tracer. And this looks like this. So we have a few different things now. So we have Trafic, we have the account service. We see the account service doing a GET request. So Trafic is obviously the configuration value we set before. The account service, that is the Flask OpenTracing library. The GET, that is coming from patching the request library. And then we can see the consumer service here, the customer service getting called. And then we can see it making SQL queries, which is the OpenTracing instrumentation library. And we can see it continuing on. So we're actually starting to get some really useful information here. So we can start identifying, we can do all the things that we were doing previously, but on a per service level. So we can start pulling out whether a request is failing, how well our application is actually running, whether requests are taking particularly long time for each individual HTTP-based service, and we can debug failing calls. We can also start really digging into which of our SQL queries are the ones which are being really crap. Which can be a real problem because sometimes you're not really sure whether an application has hit a cold start or whether you're actually hitting a slow query which you've written in your database. So I've kind of lied to you a little bit. That last trace that I showed you wasn't the same trace that we've been going through. So the last trace that I showed you was for creating a new account. This is the one that we saw the first time around. And you'll notice that it's somewhat lacking in data. This is because the cashier service doesn't make any HTTP calls. It doesn't make any SQL database queries. All it does is send an event. So there's nothing really for it to be traced other than the request coming into the system. And there are no built-in things for tracing across requests in Python, so we're going to have to implement that ourselves. It's the transaction service that is missing from this trace, which is why we're seeing so little information. So we're going to add in some custom tracing. And there are two parts to every client-server story, which is what this is. And that is the server, but also the sender. So the first thing that we need to do is we need to go to the cashier service, and we need to start adding some additional information to the events that we're sending out so that we can track them as they flow through our many services. So this is what that looks like. That code is tiny, so you're never going to be able to see it. But it is in the cashier service, in infrastructure, in Rabbit events. I talked a little bit before about how it's important to separate your tracing logic from your actual logic of the application. So I'm doing this here using the decorator pattern. So I'm extending the Rabbit broker, which is what is in charge of sending requests out to the system, and I'm extending it and creating a traced Rabbit broker. And the traced Rabbit broker overrides the method which actually sends events. So, and the first thing you can see that we're doing in this is we are starting a child span. And this is because what we want to do when we trace a request as it leaves our system is trace how long it took us to send that request. So when the request goes to the other application, we can compare it so we can see the difference between those two requests, so we can see how much latency we have between the two of them. There is something that I just want to mention here, which is the operation name emit. So there is kind of a good practice with operation names. Operation names should refer to a specific bit of your code. So emit here is fine because we only have one thing which emits events in this. However, if I emitted multiple events, I might want to scope that down so we could link it back to a single bit of code in our application. The best illustration of this I've heard is if you have a routing system, the parameters of your routing system, so for example, get customer /:ID would be an ideal operation name. However, if you go and put in the actual URL, so customers /1, for example, that is too specific. You need to be more general than that. So this is where we start coming in across the semantic convention. So we can see that we're specifying a bunch of data on our spans. So in this case, we're specifying a message bus destination, which is the exchange we're going to send our request to, the peer host name, the URL, the thing that we're actually connecting to, and we're setting a special span kind. And what this span kind means is what sort of request this actually is. So it could be HTTP, it could be RPC. In this case, it's producer, which means it emits an event. And then what we're going to do is we're going to call the confusingly named inject method. And we're going to build a dictionary that we're going to pass over the wire somehow. So it doesn't matter how you pass the dictionary over the wire. It just matters that you actually pass a dictionary over a wire to the other service. So we call inject. What it does is it injects into our dictionary, which is called headers, what the data which is in the span context. So we can get that on another server. And then what I'm going to do is I'm going to actually emit the event, and then I'm going to finish the span so that we can trace how long it takes for the actual request sending bit to take. Okay, and then the last thing that's left to do is to actually use this class rather than the original one. So we've now got events emitted with all our span data, so we can trace requests if we take that span data out. So we're going to do that now in the transaction service. Again, this is the transaction service. This is in the same place as the last one. So if you go to the transaction service in GitHub, go to transaction service, infrastructure, and then Rabbit events, then you will see this code. It's too big to see on the screen really, so I'm going to talk you through kind of what it does. Essentially, it is going to, when we get an event, we get a callback from the user. The user event, that user event actually gets called with some real data. What we do is we create a function which wraps the existing function which gets called when an event is emitted. So you can see that here with tracing callback. That's what that's doing. So when we return the tracing callback, this is what's going to be called instead. So let's kind of break this down. So the first thing that we want to do is we want to get the data which we've sent over the wire, in this case in the headers, but it doesn't actually matter where you send the data. We extract it out and create a span context from that data. And next what we're going to do is we're going to start a new span based on that data. So do you remember I was saying about how the relationships between the spans create a directed graph? That's what we're doing here with references, OpenTracing child of. So we've now got a span on our remote server which follows on from the span which was on our previous service. And again, we're following the OpenTracing convention, and we're setting all these different values. So next, what we need to do once we've got this new span is make the request context manager aware of it. The request context manager is from the OpenTracing instrumentation library, and it's what it uses to work out what the current span is. And then we call the user's real callback, and we finally start doing work for the actual user. In order to implement this, enable this, we simply start using those classes. And that looks like this. So we can now see requests as they flow all the way through our system. So we can see Trafiq, we see cashier service, and all the way through, including all the SQL requests and across message buses, which is really cool. So what can we do with this? We can do all the monitoring things we could do before. We can identify slow queries. We can debug failing calls, and we can trace trace events as they flow all the way through our system. And we can see how long it takes for our application to reach eventual consistency now, which is pretty powerful. So if we have a system and we are taking a long time to consume things from queues, this will show us how to do that. So I'm going to wrap up now. So I hope from this talk you kind of know what your options are regarding tracing. I hope you have a good idea of like how in detail a specific tracing implementation works, and you have a clear strategy for how on Monday morning or on on Thursday you're going to run into the office and start implementing OpenTracing in your office, right? You're going to do that? Yeah? Okay, cool. So thank you for being a wonderful audience and listening. I really appreciate it. It's been a great conference. Again, there's further links here to everything up there. Has anyone got any questions? Have we got time for questions? Cool. So has anyone got any questions for me? Oh. Cool. Thank you.